I would ask you, but do you guys have any questions? Let's start with your questions, and then we'll get to my questions. And I'm gonna leave, so when Amanda leaves, we're closing shop, because I gotta get to the study of broad care today. And I gotta do 3 posters, get those set up. Yeah.
I do have a question, and it's off the study guide.
Okay.
So it's under number 11. It says, we typically compare the Km of a carrier to the real concentration of the substrate of the cell. What does that comparison tell us about the carrier?
How fast how fast is the carrier working? Okay, so.
I thought the Km was the affinity, not the concentration.
Yeah, but it tells you, it does tell you. I have got to remember to bring down pencil. So let's say, okay, there's. Okay, so there's a Km. If the glucose, and let's say it's 1.5. Oh, and by the way, did anybody solve that problem that's about the GLUT1 or GLUT3 and GLUT1, GLUT2 on a handout I gave you with GLUT4? There were 2. I gave you a handout. Question number 1 had to do with comparing GLUT3 and GLUT2 in terms of transport. And then there was one about how does insulin affect GLUT4. Anyway, do that problem up above. And I think that would kind of partly answer your question. Okay? But it does tell you about rate. Okay? Because if blood sugar, let's say blood sugar level is extremely high, and one of the problems said that in the hepatoportal system, the blood sugar level is about 15 millimolar. If you had GLUT1 as in this on cells that were experiencing a blood sugar level of 15 millimolar, what would it say about the speed of GLUT1? It's probably operating fairly close to Vmax. So the difference between Km and the real glucose concentration gradient or substrate concentration does tell you something about how fast the carrier or the enzyme is working. So that's that question. I like it in terms of if this is 5 millimolar, it tells me that in the brain, sugar's getting in, even at normal blood sugar levels, but sugar is not getting in, probably very rapidly, in organs like the liver, for example, where the Km is 15 millimolar on GLUT2, and that suggests, you're probably not doing much uptake of glucose. Okay, but that problem, if you haven't solved it, go ahead and do solve it, and I think it reveals a whole lot about why the brain has GLUT3 and why the liver has GLUT2. There are other questions.
Which problem is
It's not that one. There's one, I gave you a problem, and at the back, that one, it's this one, yeah. So it's 11-13, okay? And at the bottom problem is the one we did in class where there's you're looking at the GLUT4 transporters and how does insulin affect the GLUT4 transporters. So solve that one. It doesn't take long to do it, to solve that problem. Yeah. But it really, to me, hits home on, no matter what the blood sugar level is, the brain is going to get the blood sugar.
What about number 16? It's like, how does brown fat produce heat?
Oh, okay. How does brown fat produce heat? Okay, I didn't talk about that. That was we were kind of at the end of the hour last time. Let me tell you a little bit about brown fat. Oh, down didn't say that on video. Okay. So what makes brown fat brown is that the brown fat have a lot of mitochondria. Most of the fat in your body doesn't have a lot of mitochondria, and so it appears kind of yellowishy because some of the biopigments are fat soluble, so they can kind of it can color the biopigments and kind of color the fat. Okay, but you got that tuft of brown fat back here. You were born with, and the brown fat has lots of mitochondria, so it's breaking down the fat triglycerides that it stores. Okay, and there are two ways Okay, so in brown fat, there are two strategies to get the protons back into the matrix, to move them down their concentration gradient. And I'm going to see if I can find the name of that protein. Okay, it's called UCP1. So the protons that get come out can either go back through the ATP synthase, or they can flow through this protein and not do any work. Okay? So if you feel back here on a baby, this is a good place to check to see if a baby has a fever. Back here. Okay? What is that protein going to do with the proton gradient? What effect do you think it has on the brown fat?
Gonna heat it up?
Huh?
It's gonna heat it up. Like
It's a
temperature
heat
wise?
generator. Yeah, it's a heat generator. So all summer long, bears that hibernate through the winter are actually eating a lot in order to load their brown fat cells up with a lot of triglycerides. And throughout the winter, when the bears are hibernating or winter sleeping, they keep their body warm from their brown fat, because all through the winter the brown fat will be breaking down the triglycerides, and rather than making ATP, because if they're sleeping they don't really need a whole lot of ATP, okay? The brown fat is being used to generate heat, so their body temperature doesn't drop that much. Okay, so they store that triglycerides and red fat, or brown fat, all summer long, and use it as a heat generator throughout the winter.
The protein generates heat?
No, what generates the heat? The movement of protons down the concentration gradient. The energy is going to be released no matter what. Okay? And if the energy is not used to do work, it's converted to heat. Oh, so that's right. So I was going to tell you about Bob. Okay, so this is right after my husband and I graduated from graduate school, I did a postdoc at the University of Illinois in Champaign-Urbana, and my husband worked for the Army Corps of Engineers. They had a research lab up there. So we met a couple about our age. The guy, Bob, graduated from West Point. And Bob was kind of a small, super skinny person, but he could eat like crazy. So one day we went to this all-you-can-eat place, and Bob said, "You see that fat guy over there? I'm gonna match him. Whatever he eats, I'm gonna eat as much as he eats." And of course Bob did. But Bob never gained weight, okay? So here's one way, you could probably eat a whole lot and not gain weight. We tend to not have a lot of brown fat, but some people have more brown fat than others. And they get to eat a lot of calories and those calories are not getting turned into ATP, those calories are being wasted. Okay, and there's a lot of futile cycles in glycolysis that it's been shown that people who gain weight poorly when they overconsume calories do a lot of futile cycling where they break down ATP for no gain at all. They just break down ATP. Yeah.
I don't understand how the energy is not used to do work. Like it actually makes ATP.
Yeah, that's the work being done.
Okay.
So this is ATP synthase, that as the energy is being released from the proton moving down the concentration gradient, the energy is captured and used to make ATP. In this case, the proton is just going down in concentration gradient. It's not coupled to an energy requiring reaction.
So in what case, are the three these three circles, the hydrogen moving down through those proteins, are they moving down their concentration gradient or up their?
Yeah, so this is moving up.
Okay.
This is pump,
It's the electron transfer.
this is back in. This is pump. Can you understand how this is a futile cycle? So the electron transport chain is pumping protons out, they leak back in. The electron transport chain pumps out the protons, they leak back in. This is kind of like a futile cycle. Nothing is gained except a bunch of heat. And there are other futile cycles, simpler futile cycles, where nothing is gained except heat's released. Yeah.
So could you just specify, so what is each side of that membrane?
Oh, I'm
specifically
sorry,
when
this
you're
is
looking at it?
matrix. Okay, so that's the inside, the very inside of the mitochondria, inside the second mitochondrial membrane. This is an intermembrane space. Okay, and here would be the outer mitochondrial membrane. You can just imagine it going through the outer membrane. And this is the inner membrane. So maybe Bob had a lot of brown fat and broke down glucose but generated nothing from it.
So does the brown fat not have the ATP, or does it also have that, but the hydrogen at this point?
It probably has both.
Uh-huh.
It probably has both, but there might have a higher ratio of this. And the other thing I don't know is there a higher affinity of protons for the protons on this protein than this protein? Yes.
So then would the UCP1 not be present in normal mitochondria?
Right.
Aren't in brown.
Right. Normal mitochondria do not make that protein. And it stands for uncoupled protein 1. And it's called uncoupling because you separate electron transport chain from ATP synthesis. Okay? The electron transport chain is still working fine. It's just that we're not making ATP. Now the reason why uncoupling is important, why that word uncoupling got thrown in there, because when I was in school, we learned that the electron transport chain was where the ATP was synthesized. In which case, if that was true, you could not uncouple ATP synthesis from the electron transport chain. So so the term uncoupling meant something. Kind of was reminded us again and again, is that the conventional wisdom, these guys made that ATP was wrong, and there was a separate ATP synthesizer.
So the name of that middle protein is ATP synthase, correct?
Yeah. So can you imagine what you might be learning wrong? So you are learning something wrong, probably. Yeah, maybe. Actually, Mandy.
So the concentration of protons in the matrix is high.
Mhm. Well, it's higher here in the inner membrane space, because that's the job of the electron transport chain, is to make this domain rich in protons. And I think the only purpose of the outer membrane is to hold the protons in, in a smaller region. Because there's nothing exciting about the outer membrane of a mitochondria. You can get rid of it and mitochondria still works.
So the second part of the question is talking about the dinitrophenol.
Oh, yeah,
So
that
does
one.
that fit into this one, or is that
Yeah,
separate?
that was the compound we drew yesterday.
Yeah.
It does the same thing as the proton, as this protein does.
But is
It'll
it-
also transport protons through a membrane down
Is
the
that a
cell.
separate pathway or is it the same?
Oh, it's instead of.
Okay.
Okay, so if you could have a protein moving protons down the concentration gradient, or dinitrophenol can move protons down the concentration gradient.
So the UCP1 protein is only found in, what kind of mitochondria is it found?
Oh, just in the brown fat, in the mitochondria
That has,
of brown fat.
that has brown.
Yeah, you probably would not find that protein in the mitochondria of your muscles, because that would be a bummer,
Just because you need that energy for.
or anything else. Huh?
Because you need that energy for contraction, you don't want to waste it on
Right,
heat.
that would be a bummer. To burn and crash pretty quickly. Okay, do you have any other questions? Yeah, Ralph.
For number 15, it asks like describing the E1 and E2 states.
Mhm.
What was I remember, I don't know what it was called, but I remember you drawing it yesterday. What was the step that was blocked by digitalis?
Okay, so does anybody remember, is it E1 or E2 phase that gets, is the sodium potassium pump locked in?
It's going from E2 to E1.
Yeah, so it's stuck in the E2 phase. Okay, so in other words, the digitalis is essentially blocking the release of the phosphate. So the sodium potassium pump remains phosphorylated, and so it remains stuck in the E2 conformation. And Wabang does the same thing.
So,
Yeah.
The only molecule that we're gonna have to draw on this is like a phosphatidyl something, right? We're not
That's the
gonna
only
have to
thing, right.
draw Amino
right.
acids or
Yes.
anything right now, okay.
I want you to be able to draw that just to remind us, because we're gonna, of what a phosphatidyl this or that is, because we're gonna encounter phosphatidyl this and that's later on in probably unit 3, because they're second messengers in cell signal.
Do we need to know how to draw the possible markers?
No, you don't need to know how to draw the R groups. If I have if I list some amino acids, I will tell you whether they're hydrophobic or hydrophilic. I'll give you or I'll just plain give you the structure. Okay? So don't memorize amino acids. Did you do that in biochemistry?
Yeah.
Do you remember them?
No.
Okay. And that's reasonable, but once you start in this, start looking at cell biology and maybe more biochemistry, pretty soon you realize you just know because they get phosphorylated or glycated, and after a while, you just know the structures of those amino acids. Yes,
I'm still kind of lost in the heat generation. Like, I thought the energy is stored between between the phosphates and the ATP, right?
Yeah, ask that question again, Laura.
Like, energy is stored between the bond, the bond between the phosphate group and
Right.
the adenosine. Between the phosphate bonds. But how are you releasing that energy when you're actually making ATP with the ATP synthase?
How are we releasing, or?
How is the energy lost to heat when ATP is actually being made?
Oh. The mechanism of energy transfer here is really complicated. But what we're doing is storing, so the energy that was used to be a proton gradient is now stored as chemical energy. So this used to be electrochemical gradient, but it's being stored as a chemical gradient in the bonds. But I'm not sure I'm answering your question.
Since energy is stored in the chemical, as a chemical energy, how is that converted to heat and the heat that is generated?
Oh, okay, so if this goes downhill, and energy is released, it's not used to do work, it is just still energy released, but when it's not coupled, the energy is heat energy, thermal energy, random molecular motion energy.
Okay. So if you want us to explain this in the test, we'll just pretty much talk about how they use CP when pumped hydrogen out of the intermitochondrial space, which could have been used to generate ATP, but it's used to generate heat.
Right. Okay, go back to, what you want, can you go back to the picture of the rock falling down the hill? Okay. So that one, remember that tells you the secret of life and stuff? Okay. So the very first picture, okay, is this situation. Okay, so remember, so the rock or the proton are going down they're going down either an energy gradient or down the hill in an energy releasing reaction, but all of the energy is released really as heat and entropy. Okay? When those protons are forced through the ATP synthase, that would be this second picture where the energy is going to be released no matter what, but we couple that energy release with ATP synthesis. Okay, so this is kind of this is also considered a coupler, is that we're not coupling the release of energy with any work being done. And that has nice consequences to us, because really it does keep you warm. And babies have to rely on that for a while, because they're not moving around as much and generating heat. Because I think most babies should be sleeping.
So could you talk a little bit about how the test is going to be structured? Is it going to be all essay? Is it essay and some multiple choice? How is it going to be structured?
Okay, I will do that, and Matt, then I'll get your question. So the test will, I'm thinking molecular genetics. Molecular genetics does have a matching. Let me tell you one type of question that people who've had my courses before know this is coming, and if you've never had my course before, you don't know this is coming. There's going to be a significant question. Now, I'll say this also, I'll say maybe Okay, and let's say okay, we'll do this one. Well, this is really, I would never use this one. Okay, I would never pair these together and ask you because it's way too obvious. Okay, so when I ask for a significant similarity, if you say, oh, they both transport glucose, that's not significant because GLUT1, GLUT2, GLUT3, and GLUT4 also transport glucose, but I asked you about these two proteins. What do these two proteins have in common? Okay, so I think I will, and I may or may not have it on this particular, but that's a pretty standard question. So you have to think about how these two proteins specifically are similar to one another. And if you say, well, they're both involved in transport of small molecules, well, so are hundreds of other proteins. So that's what I mean by significant. If I consider it insignificant because I could say, well, SGLT1 and then list a whole bunch of other proteins that would fall under the category that you listed, then it's wrong. Okay? Significant difference, that's probably much easier. Okay, SGLT1, and you could tell me one's found in the kidney, one's found in the kidney intestines, and that's okay, but I didn't ask you where they were found. If you say SGLT1 transports 2 sodium per glucose, and SGLT2 transports 1 sodium per glucose, that would be a great answer. Okay? But where you're gonna get probably caught is telling me a similarity that yeah, that's true, but you could say that with for a whole bunch of combinations. Okay, so as you see those things, so why are these two proteins specifically, and not some other two proteins put together? And that will help you out. That'll take you a long way. So there'll be that. There probably will be some matching because that gives me something that if I'm really getting tight on grading, I can hand it to my husband and he can grade it. But I usually figure this will take me 10 minutes to grade this problem. I can just move through those pretty fast. There will be a delta G problem, but I'll provide all of the concentration information. Does RT equal? What does the Faraday constant equal? So I'll give you all of the stuff you need, and you just end up plugging this stuff in, plugging numbers into the equation appropriately.
Are you gonna give us the equation too?
Huh?
Will you give us the equation too? Or-
No.
Okay.
No, I already did. It's on your. There's a handout. So, there will be new, maybe novel transporters that we haven't talked about before, but you should be able to, I'll give you enough, ask a question about it, and you'll have enough information to be able to apply what you know to describing a new transporter or a drug or something, just something. But there's going to be some application. But you will have the correct information already at your disposal to answer that question. So I would say most of it is not going to be application. And if I have an application problem, it will probably be not worth as many points as a spin-back problem. So in other words, if you just are the type of person who thinks that learning is memorizing everything under the sun, you should be able to do okay. Maybe not an A, but you should be able to do okay. Okay, if you don't understand the material and you didn't really memorize anything, then you probably won't be doing all that well on the test. Okay? Is there anything else you want to know, Kayla? Okay, I'm going to get Matt and then Autumn, I'll get you.
On number 19, on the study guide, do we have to talk about ACE inhibitors?
Oh, no, we didn't do ACE inhibitors or what?
Yeah.
Really?
Yeah. Do I have a different one than everyone else for some reason?
No.
What, 19?
19. The very last
I
one.
definitely think you.
Distinguish between, my number nine, this one, number 19, distinguish
Yeah.
between the calcium pump and cardiac muscles, that would be the calcium. How did you get that?
I have no idea when I got this.
My
did
number
you print
19
off
is
the
the same
new
one as yours.
I mean, I printed it off a long time ago.
Really? Oh, you probably did, and I replaced it.
Oh, okay.
I did replace it.
Then never mind. We're
So,
good.
never mind, just go back, just go to the Scholar and get a current copy. I did replace, yeah, not to mention it, I did replace the study guide. But there used to be, used to look at, a group of diuretics. So, and I have no idea why I put these in here.
Everything else on it's good.
Okay.
Yeah.
Well, the pictures, I updated the pictures, the figures to pay attention. I think I probably did.
Do you have this in one, or no?
Oh, I changed some of the vocabulary.
Yeah, I didn't know it.
Yeah, Carly.
Could we go through just this and have like examples?
Oh, we are, and I'm not telling you the examples, but
Okay.
if we have time, that's what we're gonna do.
Okay.
Autumn, do you have any questions?
Well, I just wanted to go back to the significant similarity and significant difference. So, for significant similarity, if you mentioned they were like the same type of transporter located and then that's on that intersected link, or you want to be more specific?
If you told me they were both located in the nephron, that's still not significant because you got SGL, you got GLUT2. So if you said, these are both sodium glucose importers, they both use sodium, to release the movement of sodium down its concentration gradient to drive the pumping of glucose up a concentration gradient, that would be great. Okay, but to say that they're both in the kidney, there's other glucose transporters in the kidney too. So, okay, so I'm gonna get that picture out. Yes, hold on, I couldn't remember who had
For number
the
19, I mean, what is the significant difference between the calcium pump in cardiac muscle and that in skeletal muscle?
Okay, that's a good question. So the transporter, calcium pump in the cardiac muscle that I'm thinking about is the one on the plasma membrane.
Is it circle?
Huh?
Wait, is it the one we talked about?
Yeah, we talked about it.
So circle is the skeletal muscle one.
Circuit is a skeletal muscle, one, and it's actually found also in cardiac, but it's the only one in skeletal muscle, okay? And it's an ATPase. And what's the energy source for the calcium pump in cardiac, plasma membrane of cardiac cells?
So sodium calcium sulfate?
Sodium.
Hmm?
Is it sodium potassium?
Yeah,